Good afternoon and welcome to this webinar, Emergency Lighting and Power Application 101. Don't get lost in the dark. This event brought to you by Mission Critical, sponsored by Eaton. I'm your moderator, Caroline Fritz, editor of Mission Critical. Thanks for joining us. Today's presenter is Ed Spears, Product Marketing Manager for Eaton's Critical Power Solutions Division in Raleigh. A 35-year veteran of the power systems industry, Ed has experience in UPS systems testing, sales applications engineering and training, as well as working in power quality engineering and marketing for telecommunications, data centers, cable television, and broadband public networks. Don't forget to submit your questions, and later in the program, Ed will address as many as possible. Today's event is being recorded and archived on missioncriticalmagazine.com. And now I'm excited to turn it over to today's presenter, Ed Spears. Welcome, Ed.
Thanks, everyone, for taking time to visit with us today. And let me let the moderator know that I don't have slides showing on my computer, but let's go ahead and push the slides manually. And our topic today is emergency lighting and the use of UPS systems for emergency lighting backup. So let's get a quick definition here if we push to slide 2, and a little description of a UL924 UPS. Now, UL924 is the listing or the standard that Underwriters Laboratory uses for UPS systems that are intended for emergency lighting. It should be understood that this particular type of system is only used for emergency lighting. In other words, if I have a UPS system that I'm using for data center backup or something along those lines, then I cannot use that same UPS as part of my emergency lighting backup system. So we want to be aware of that, and we'll take a quick look at our agenda, which is on the next slide. We're going to get a quick overview of the market here, talk about safety requirements that emergency lighting systems dictate, the types of different emergency lighting systems, because there's several ways to do this that are acceptable to the electrical code and fire code, etc. If I have relatively small lighting systems for a small to medium-sized building, that's generally going to be less than 20 kVA in terms of total UPS power. If I have a larger building, a multi-story office building or a large factory, for example, or even something like a stadium or parking area or something that uses high-intensity discharge lighting, that's typically going to require a bigger UPS system. So the next slide shows the kinds of marketing or the type of markets that we serve. Certainly commercial buildings, both government and private buildings, office buildings, etc., are a big user of emergency lighting. It is required that these systems be in place, just like fire alarms and things like that. Multi-residential buildings, i.e. apartment buildings and hotels, healthcare applications, hospitals, clinics, those type of things, even mobile applications. And of course, data centers use emergency lighting as typical commercial buildings as well. But primarily, emergency lighting UPSs are used outside of a data center application. So next slide. Why use a UPS for emergency lighting? If you're familiar at all with this, you're used to seeing the little white or beige or dark boxes on the wall that have a couple of lamps on them, and they light up automatically when utility power fails so that I can see to exit the building, navigate dark hallways, and find the proper way to the exit. And it's not just the hallway lights and those type of emergency lights, but also the illuminated exit signs that basically are showing me how to get safely out of the building through multiple pathways if I need to during a power-related emergency. Now, generally, it takes a lot of these little wall-mounted boxes to properly light a commercial building, for example, and the number that you'll need depends heavily on the type of application or the type of building you're supporting. If my building is a factory and I'm lighting a factory floor, that's going to take a certain number of these little portable, or not portable, they have to be permanently installed lights. If I'm supporting an office building, then of course I need emergency lights in the hallway at multiple locations along the hallway. I need a certain amount of lumens available. I need to have a light every time the hallway makes a turn. So anytime the person has to turn a corner to exit the building, there needs to be a light at that location. There needs to be exit lights and exit signs at each doorway. There need to be exit light or emergency lights in the bathroom, for example. So it takes a lot of these little guys in order to properly provide emergency lighting, especially for a large building. we may be talking about very roughly one of these lights for about every 1,000 square feet. And the good news is, a couple of things, these portable or these small emergency lights now use LED lamps instead of incandescent, so you're less likely to have issues with bulbs burning out and things like that. And even with their internal batteries, which are now much smaller, lighter, and more compact, these type of devices purchased in volume are down around about $20 to $25 each in terms of purchase cost. Now there's costs associated with installation and things like that. So those are called standalone systems or wall-mounted emergency lights. Generators is another way to meet the emergency lighting application. Technically, if you have a generator in your facility that's located outdoors and can start and stabilize in about 10 seconds, then the generator can function as your emergency lighting support and backup for that building. But if the generator is located in the basement, for example, or inside the building where it may not be able to be reached in a fire or something like that, or if the generator takes more than 10 seconds to start up and stabilize after a power outage, then you're going to need a UPS in addition to the generator in order to have an appropriate emergency lighting backup system. Now, there are devices out there called emergency lighting inverters, and these are not technically UPSs. It's a inverter which takes DC power from a battery and creates AC to drive building lights, but it has only a small battery charger to recharge that battery in a reasonable period of time, usually about 48 hours. Now, there's several third-party manufacturers that make these. Some of them have been in the business for a while, but there are concerns about the availability of service and the ability to communicate remotely with these devices if a problem happens when I'm not in the building. So moving along to the next slide, the UPS-based emergency lighting offer NFPA 101 certified solutions that address emergency preparedness requirements and other building standards. So unlike the alternative possibilities for emergency lighting, a true UPS is going to offer, first of all, a more aesthetically pleasing solution. That means the UPS is in a closet or a basement somewhere, and I don't have all the wall-mounted emergency lights to deal with or paint around or test on a monthly basis, etc. So centralized methods do allow us to meet regulatory requirements, and they vastly simplify the monthly and yearly testing that's required of the entire emergency lighting system. And of course, they're backed by large factory-trained service and support organizations who are used to being able to come out and service a machine within hours, not on a next-day basis or on a next Monday basis kind of thing. Okay, emergency lighting requirements. NFPA 101 is concerned with life safety. What we're doing is making sure primarily that people can safely exit a building in a lighting or in a power emergency where it would otherwise be too dark to find your way out. So NFPA 101 dictates whether emergency systems are required and where and how many emergency lights need to be located, how much light in lumens needs to be provided in order to adequately light an egress path from a building. Now, NFPA 110 concerns itself with emergency and standby power systems, like you might find in a hospital, for example. So that's both things like UPSs, but also things like generators and power systems that are necessary to keep things running and keep the commercial facility or building in some level of operation for an extended period of time. Now, in the National Electrical Code, Article 700 talks about the different types of power sources that are required, and we'll see a little bit more of that as we move along. So looking at NEC 700.12, the typical emergency lighting designs, there's several ways to do this. I can use a simple storage battery that I recharge and run my emergency lighting off of DC power from that battery. That's relatively uncommon except in large battery-intensive facilities like telephone central offices, for example. Generator set is much more common, and again, if the generator can start and stabilize quickly, it can be the source for emergency lighting backup. The UPSs are uninterruptible power supplies that we'll be talking about in this presentation. There's also separate services, and by that they mean separate utility sources for a building. So in a large building, I might have a utility feed on the northwest corner of the building and a different utility feed on the southeast corner, so that I have two possibilities for power to that building. If something happens to one of them, the other one is still there and can provide services like lighting, airflow, HVAC, elevators, and all the emergency needs for that building. Less common would be a fuel cell system. Now, fuel Fuel cells are becoming a little more frequently seen in some large facilities, especially data centers, and they have the benefit of being very green and sustainable. They only emit water and heat in their process, so they are very environmentally friendly, but they are significantly expensive, and they do require some special considerations when installing and setting up. Now, unit equipment, part F there, that's where they're talking about the wall mount exit signs, the wall mount emergency lights. In the blue box at the bottom of the slide, there is a special consideration that we should note. It says for buildings higher than 75 feet tall or buildings that house greater than 1,000 persons of designated occupancy, then secondary sources A through E, whether it's a storage battery, a generator, UPS, or whatever, require to be located in a conditioned space with fire suppression and a 1-hour fire rating. So that means the walls of the room are going to have a 1-hour rating, as are the doors and any windows. And if you're familiar with these types of installations, it can add a great deal of expense to your building when you put in a room with at least a 1-hour fire rating. But that is required no matter what source you use for emergency lighting. So let's take a look at them real quickly one at a time. The storage battery alone, the NEC requires that battery lasts for 90 minutes. That's a lot longer than we're used to in UPS applications. So at least an hour and a half. There's a few cities that still require even longer than that as a part of the local code. The battery is required to have a properly sized charger. What is that? It means it can't take 2 weeks to recharge that battery. Typically, they're going to be looking for about 48-hour recharge time, at least, on a 90-minute battery. The battery cells themselves, the actual container that the battery is in, if it's a sealed battery, then those cells can be made of opaque plastic or Lexan or whatever acid-resistant material that's intended. If it's a flooded electrolyte battery, meaning the kind of battery where we have to add water to on a regular basis, those batteries need to have either a translucent or a transparent case so that I can see the level of liquid inside and know when I need to add water. Much more common to see sealed batteries rather than the wet cell type for this application. But in an extremely large building, you might see wet cells. The electrical distribution of this DC power must be properly connected and distributed to all the safety loads per the NEC requirements. So this is going to have different rules and requirements and guidelines and standards than traditional AC electrical distribution, and the installer and the authority having jurisdiction must be familiar with what those are in order to provide a proper and safe and protective installation. The next one is a generator set. Remember, a generator set can function for emergency lighting by itself if it's the type of generator that starts and stabilizes within 10 seconds. And that's not uncommon for a small generator like you see in the picture here. Keep in mind that if I have a large building and a big old diesel generator sitting out back, I am going to be concerned that I don't necessarily want to fire up that giant generator every time there's a tiny blink in utility power. And if I'm really going to meet that 10-second requirement, like I have to do in a hospital, for example, that's going to require a lot of technically unnecessary generator starts and stops. But that is the requirement. If the generator takes longer than 10 seconds or is delayed, say 30 seconds before it attempts to start, then a UPS is going to be needed to bridge the gap and make sure things like lights and other critical devices work during the time the generator takes to start. So a couple of points here. NEC listed prime movers. If you're not familiar, prime mover is the NEC's word for motor. It needs to be acceptable to the authority having jurisdiction, size per NEC 700, and I need a means for starting that motor on failure and with a retransfer delay, which means I need a battery so that I can start that motor by remote control or automatically when we sense a utility power failure. And before we come off of generator and back on to return to utility power, there needs to be a programmable delay. Why? So we can have a few minutes or seconds at least to make sure that the returned utility power is in fact going to remain on and stable. So the engine must have on-site fuel supply for about 2 hours. Even though the technical requirement for backup time is 90 minutes, they still require fuel tanks either in the base of the generator or even underground for at least 2 hours of full expected demand. So the generator can run for at least 2 hours on its designated fuel. Other requirements: fuel supply for the prime mover, battery power, and air dampers. Now, air dampers, if you're familiar with large generators, will typically be manually or usually automatically opened. They're louvers like you would have on your shutters at home, that allow free air to flow into the generator enclosure when the generator is operating. If these don't open or fail to open for any reason, it's in fact possible that the generator within 2 hours can overheat and shut down, and we do not want that to happen. So air dampers that operate automatically are either preferred or required. Auxiliary power supply, a backup start battery, something along those lines to make sure or help ensure that that generator starts every time without exception when the power fails. There is an outdoor location requirement, and again, we mentioned this earlier, we want to make sure that the generator is located ideally outdoors of the building and not in the basement or in an equipment room, because if the building is involved in a disaster like a fire, we want to be able to access the generator if we have to manually start it, for example. Okay, looking at the next slide here, we get to uninterruptible power supplies, which are the products that we want to talk about primarily here. And for UPSs, the NEC requires that the UPS meet all the applicable requirements for both the storage battery and the generator set. We just went through those. And there's also the UL 924 auxiliary, sometimes known as UL 924A for auxiliary. Now, UL likes for us to call it UL 924 auxiliary, so that's what I'll try to do. But that's using the UPS with perhaps a 4 or 5 minute battery backup time to bridge the gap while the generator starts. So if I'm supporting loads like, for example, high intensity discharge stadium lamps, I know that those lamps, if I interrupt the power even briefly, they're going to go out. And if the power comes back in a half a second, it's still going to take 30 to 45 seconds for those lamps to restrike and turn back on at full brightness, just like the old-fashioned street lights. We know that those are being quickly replaced by high-intensity LED lamps that have longer life and better brightness control and things like that. But for those types of HID lighting, it's a good idea, if I'm depending on the generator for long-term backup, to have a UPS that instantaneously provides support to that lighting so I don't have to deal with a restrike delay. So outdoor lighting like you might find in a parking lot or a parking deck is another example of this type of application. Separate utility services. This is what we were talking about briefly a moment ago, where I have multiple utility sources to a building. This is not common unless it is a mission critical application like a data center. Hospitals are another application that would be at least a possibility for having separate utility services. And the idea is if one utility service fails during a thunderstorm, for example, the other utility service can power that building. So it means they need to be truly separate. I need separate conductors at 2 different places in the building, and I'd like for them to be sufficiently remote, both electrically and physically, to minimize the chance of them both failing or being interrupted at the same time. For example, a fault on one service or a short circuit on one service should not bring down the other service, if at all possible. So we're all looking for the ultimate redundancy here. Fuel cell systems, just a couple of points here, because these are relatively uncommon for emergency lighting. But the NEC Article 692 does specify circuit requirements, what kind of disconnecting means. Remember, a fuel cell is typically a DC output device. So that dictates wiring methods that are special or specific for these types of products. Marking for the fuel cell and for the distribution points themselves, how it's connected to other service, and special requirements if the output is over 1,000 volts, which is typically not the case, but it can be. Now the last one is the wall and ceiling mount equipment that we talked about before, and the requirements for those is that the battery needs to be rechargeable. And traditionally, these were relatively large and heavy batteries that dictated the entire size of this wall-mounted box. But if you pull a new one off the wall today, you will open it up and see that it has a relatively small nickel metal hydride or even a lithium battery that often runs as much as 2.5, 3 hours instead of the 90-minute minimum, and is relatively small, lightweight, and easy to replace. So that's the good news. But each one of these devices has to be tested every month to make sure that the lights work, that the battery is good, and the battery charger works. And if I have 200 or 300 of these in a medium-sized office building, maybe a 4-story building, for example, then that's going to take a small crew of people a half a day to do that, and has to be done every month. And the cost of that can be surprising. So they need to have a rechargeable battery, a battery charger, and 1 or more lamps attached. We find that most designers and most manufacturers make these with at least 2 lamps. It's very unusual to see one with only 1 lamp. That's a holdover from the incandescent light days when the 1 lamp may burn out. Nowadays, they're LED lamps, which have the benefit of longer battery life because they use less power, but they're much less likely to burn out on an average lifetime basis. And there needs to be an automatic device that energizes them, a relay that automatically senses a power outage, turns on the light. And they need to be installed per the installation requirements that are dictated in NEC 700. So these all have to be wired to 120 volts AC typically. So that's extra wiring in the building, which is dedicated to emergency lights only. So that needs to be considered if you're comparing the cost of a UPS centralized system or a wall-mounted secondary source equipment like we're talking about here. Okay, so if I am considering a UPS for this, for a UL 924 application, emergency lighting, the UPS offers a centralized system where you have all of your maintenance done in one place. For example, monthly maintenance, instead of being done on several hundred wall-mounted devices, can be done in one UPS. And by monthly maintenance, we're talking about coming up to the UPS and removing utility power and verifying that the lights stay on and the UPS does in fact run on its batteries, and then returning utility power and verifying that the battery charger does start and begin to charge the battery. So that's one test, takes place in just a few minutes on one device. That's to be compared with wall-mounted emergency lights. I may have hundreds of them in a building and they all have to be subjected to the same test. I mean, somebody has to go around to every emergency light, push the red button, verify that the lights come on, let go of the red button and verify that the charger comes on. And again, depending on how these are mounted, that may require moving a ladder from place to place or using an extension or something like that. But overall, it's a lot more labor intensive. The UPS offers a little better ease of maintenance because of the ease of access and the fact that I have one device that may power 10% of the lights in the building. It also allows me to avoid a generator system if I don't need one otherwise. A UPS with 90 minutes of battery backup is going to be pretty big and heavy. However, compared with the cost of adding a generator that I don't need otherwise, a UPS is a much more cost-effective installation and much less expensive to operate over the long term. Or I can use the UPS to supplement my existing generator, so in this case I would not need a 90-minute battery on the UPS, only a 4 or 5 minute battery while the generator starts and stabilizes. So how do I size a UPS for emergency lighting? Well, the answer to that is wildly varied, as you can imagine. But let's just pick a rule of thumb here so you can get an idea. In a typical commercial building, it might be an office, it might be a warehouse, it might be a factory, it might be a hospital. But in a very average general situation here, we could assume about 1/4 of a watt of UPS capacity per square foot. So if I have a 5-story office building or 100,000 square foot factory, we're talking about 100,000 square feet times 1/4 watt per square foot, I'm going to need about a 25 kilowatt UPS. And that UPS needs to have enough battery to support 25 kilowatts for 90 minutes minimum of runtime. And I need to be able to recharge that battery from a full discharge in about 48 hours or less. So the UPS would be connected to a dedicated panel, and that panel would feed, let's say, 5% of the existing overhead light fixtures in that office building, which means when utility power goes off, all the lights go off except the ones that are powered by the UPS. So they are chosen in advance to be the ones that will light the hallway, provide lighting in the restrooms, even in elevators and things like that, so that people have a way to visibly see how to exit the building. The good news is I'm going to wire up those lights anyway as a part of the building lighting system. The only difference here is I'm feeding my emergency lights with a UPS and a dedicated panel that handles just emergency lighting. So I need to perform selective coordination on those breakers upstream of the UPS and between the UPS and the distribution. And if the UPS transfers to plain utility power on an overload or failure, then the downstream distribution needs to be coordinated with the utility breakers that are associated with the UPS. This is not an option. Until recently, relatively recently, it was not a requirement to coordinate here. But for safety reasons, I do not want to fault or a short circuit downstream in the distribution to cause a main breaker to open that dumps all the emergency lighting in that part of the building. That, of course, would be a disaster. So I do have to selectively coordinate the circuit breakers and or fuses and protective devices that are in line with the critical lighting devices that I'm supporting. Here's an example for a small building, let's say 50,000 square feet or less. Now in a building like this, the lighting voltage is likely to be 120 volts, just like in your residence. So for 50,000 square feet, roughly a 12 kilowatt UPS would be required, and that's what we show in the picture here as an example. This particular example is about 48 inches wide, 48 inches tall, and 34 inches deep. Notice the weight here, over a ton of battery here for a 50,000 square foot building. And if you look at the picture, you see it looks like 9 identical black blocks. One of them is the UPS electronics, rectifier, inverter, and battery converter. The other 8 of them are crammed with batteries. So it's relatively compact for 90 minutes of backup, but we're still talking about a very heavy device. Hopefully we'll be able to talk to our clients soon about lithium-based batteries that will save probably 40 to 60% in both the weight and the size, but not quite available yet. So moving on, for larger solutions, we generally recommend a modular UPS that allows the customer to pay as they grow. If they add an extension to the building or a new wing to a hospital or something like that, I'd rather not rip out the emergency lighting system and all those batteries and have to start over again with something bigger. So, for example, on this page you see UPSs with ratings of 40, 80, 120, or 160 kVA. So I can start out with 40 and slide in an extra 40 into an existing enclosure and maybe add some batteries, but it allows me to build on the emergency lighting system that I have without starting over again with something larger. I do need to think about premises wiring that feeds that UPS to make sure I have enough capacity to handle that UPS no matter how big it may grow over the years. Typical things that you'll see specified in this type of system: output power factor 1.0, so the kVA and the kilowatts are the same. Remember, your loads may be lighting ballast for fluorescent, and you want to think about what the power factor is and whether it's leading or lagging. Most modern UPSs can handle it either way. It is more common in larger buildings to see 277 volts instead of 120 volts for lighting, especially in large buildings where I have an acre of factory floor, for example, and it becomes a lot more economical to wire my lighting at 277, especially since I already have the 480 volts for other mechanical devices in that building. So in our particular case, we use 40 kilowatt power modules that can be basically slid in and increase the capacity or add redundancy to an existing system on an as-needed basis. So I start with what I need, and I add only if and when I need more capacity or if I need redundancy. So I have scalability, a little better serviceability, and the ability to provide N+1 redundancy in my lighting backup system without having to buy a whole second UPS and a whole another large 90-minute battery system. In medium to large buildings, this is an example of what the UPS would look like along with basic battery. The battery could be larger depending on the actual size of the UPS. This is a 20 kilowatt load, so it's not a huge UPS. Most of that black box you see there is battery, for example, and you see the dimensions: 56 wide, 74 tall, and 42 deep, and the weight now is up over 2 tons for that UPS. In a large building, UPS is almost always 480, 277 volts, and the lighting is being operated phase to neutral 277. This shows a 120 kilowatt UPS. There are UPSs available up to 200 kilowatts, and maybe a few of them even larger than that, that are intended specifically for emergency lighting use. So the physical size of the machine gets quite a bit wider, and look at the weight there. So now I'm up to 20,000 pounds here for a system that is bigger than the box shown here. This box shows the UPS alone, not all the battery cabinets that need to go with it. So again, the upfront cost to purchase and install this type of system is probably going to be considerably more than buying 3 or 4 or 500 wall mount emergency lights. However, the total cost of ownership over the service life of the equipment, because the monthly and yearly discharge and maintenance is much, much less expensive and much less labor intensive, is going to allow you to end up with savings on the testing processes. But not only that, the installation and wiring costs are going to be actually dramatically less in terms of wiring the downstream distribution and the existing building lights that you are going to wire anyway, whether you feed them with a UPS or regular utility power. Okay. So this shows a picture of a medium to large solution and the 34-inch wide battery cabinets that go with it. to give the 90 minutes of battery backup time. So this shows you what part of the system is electronics, i.e. the black box on the left, and the two other cabinets there are battery cabinets, and you see they're each 34 inches wide. And by the way, each one weighs about 3,300 pounds, and it would not be uncommon to see up to 4 cabinets on there. What about a maintenance bypass or a wraparound bypass? This is something we recommend with most of our three-phase UPSs, and the reason it's there is to allow the service person to work on the UPS with the entire UPS completely de-energized for safety while still providing power to the output and the mission-critical loads on that output. So a maintenance bypass can be UL 924 compliant as an option for the UPS. It allows service while the load continues to be supported. It even allows the load to be supported while the UPS is exchanged for a new one, for example. So those are good reasons to deploy a maintenance bypass, otherwise known as a wraparound bypass, with a UPS for this application. So it's recommended but not required. Okay, in the next picture, we talk a little more about, or we see a picture of the scalability I was talking about a couple of slides ago. This particular UPS is built on 50 kilowatt or 40 kilowatt blocks, depending on how much battery charge capacity we need. So this is basically the shelf, or the container itself has 4 shelves, and I can populate with 1, 2, or 3, or 4 power modules. So if all I need is 50 kilowatts on day 1, I can populate just 50, and I pay a lot less for the upfront, and the battery is going to be considerably smaller as well. But if my building grows or my application grows, then I might need to put in another 50 to make it a 100 kilowatt UPS, or a 150, or a 200 kW. Remember that if I add power capacity, I'm probably going to be adding battery strings as well. So allow the necessary floor space for this UPS to grow to its full capacity, even if that doesn't happen for multiple years down the road. Typical system manageability. As compared with the alternatives for emergency lighting, a UPS system is going to provide front panel and remote monitoring capabilities with a lot more detailed information and monitoring and controls that you would see with a typical piece of emergency lighting backup. So we can see tabular information, status alarm logs, metering information. For example, if I want to know what the output voltage is, and I want to know how the output voltage has varied for the last 24 hours, or the last week, or the last month, or the last year, I can get that information both in a table and as a graph right on the front panel of the UPS or via remote monitoring. If I want to know the status of my battery at 3 o'clock in the morning when a thunderstorm is approaching, I can see the status of each one of my battery cabinets and have a good estimation of how much battery backup I'm going to have at current lighting loading, and I can basically do things like manually start a generator that didn't start automatically, for example, based on some peace of mind that I know the UPS battery is going to operate long enough to provide the necessary backup while I get the generator started. So it gives you more flexibility and a lot more knowledge about what's going on inside the UPS. And today's UPSs, whether for emergency lighting or data center backup or process control, factory floor automation, they all have much better connectivity and monitoring capabilities, can typically be done over the internet. All you need is a web browser and a communication card to snap in the UPS, and I can see a wealth of information about the UPS, both in real time and past information in the form of data logs and alarm history files and that type of thing. So lots of possibilities, and they'll work in a variety of networks. If my building uses Modbus for most of its infrastructure monitoring, the UPS can provide that kind of connectivity or that kind of protocol. If they'd rather use BACnet, or if it's a data center and they'd rather use SNMP, for example, the answer is yes to all of those. From most UPS vendors, they can communicate using whatever protocol that the client chooses. Another thing that you'll find in modern UPSs is some capability for predictive analytics. Most remote monitoring systems that you're familiar with basically wait for something to break, and they monitor that and tell the user that they have a problem. Well, that's not always ideal. The user would like to know before the issue occurs. So predictive analytics, which is now available in some of our products, allows us to monitor the data from literally hundreds to thousands of UPSs and give us a good indication of if we see something that's trending in the wrong direction, what is the risk or the likelihood that a problem will occur? And if it does, then we want to make sure that we react prior to the issue by scheduling a maintenance window to replace something like a fan or a capacitor or any of the consumable devices within the UPS. So we're more proactive here. Instead of waiting for something to happen and have to do unscheduled maintenance, we'd rather let the client know in advance so that we can schedule together a convenient time to do this kind of maintenance. So predictive analytics allows this to happen, and it uses things like the Internet of Things and big data analysis from many products. We're monitoring nowadays 300 sensors every 15 minutes from thousands of UPS products located around the globe. So you end up with huge databases that allow us to predict the risk with some level of accuracy. It's impossible to predict that something will fail at a certain time, just like you can't predict an earthquake. But it's nice to be able to know in advance if something's trending in the wrong direction and needs attention before it develops into an actual problem. So as we wind it up here, there is a new market that we mentioned earlier called UL 924 auxiliary, and this allows, if the generator is already on site or if the client would rather use a generator rather than large 90-minute battery backup, the generator, if it operates and starts and stabilizes within 10 seconds, then the UPS can be used in conjunction with that generator to make sure that our HID lamps and things like that do not need to restrike. But if the generator is fast enough to start stable within 10 seconds, then I may not need a UPS system at all. But for most large buildings, they don't want to cycle the generator every time the utility power blinks. So the generator will have a 30-second or a couple of minute delay before it starts. In other words, the power has to be off and stay off for a period of time before the generator starts. So in that case, I need a UPS with just a few minutes of battery backup to keep the emergency lights operating until the generator comes on and takes over the long-term backup. So that's quite a bit of good news from the standpoint of not having to buy a lot of big, ugly, heavy batteries, but it also means that I'm going to need a generator. A lot of commercial buildings already have a generator, so that means they can be compliant with UL 924 for emergency lighting without having to buy 90 minutes worth of battery for their UPS. They can get away with a much more palatable 5 to 10 minute battery, maybe even a little less than 5 minutes. So a couple of frequently asked questions here. Are UL 924 emergency run times besides 90 minutes offered? Other than the UL 924 auxiliary, most UPS and emergency lighting vendors will offer 90 minutes or 2 hours, usually not more than that. The UL guidelines that we have to test to achieve UL 924 compliance are based around 90 minutes. So the answer is really, as a standard product, we're talking about a 90-minute battery backup. Can I use a regular data center UPS in place of a UL 924 system? There's another couple of things that are different besides just the longer battery. The controls of the UPS and the bypass controls in particular need to be designed so that the user cannot inadvertently transfer the UPS to plain utility bypass and then forget to put the UPS back online. Because if they do that, then of course a subsequent power outage will result in all lights going off. So locks and barriers are put in place so that the UPS cannot be inadvertently left on bypass. You know, somebody comes in for maintenance and forgets to put the UPS back online when they're done. They require some physical devices in the UPS and some physical barriers so that an untrained person can't inadvertently transfer to UPS to bypass, for example. So there are some different hardware in these type of UPSs, and the documentation and the manual describes step by step the monthly test that needs to take place every 30 days and the yearly full discharge test that needs to take place as well. Question 3 here says, do all centralized systems cost less than wall mount? Particularly in small buildings, I would not assume that at all. In many cases, a wall mount is certainly going to have a lower upfront cost. However, you want to take into account the labor cost to do that monthly testing over the full lifetime of the system, which could easily be 15 to 20 years. The last of the FAQs in this section, before we open it up for general questions, is should a UL 924 UPS be UPSbased certified? Now, if you're not familiar, that is the seismic certification that developed originally in California and has been widely accepted in other states in the Union here in the U.S. and requires, for example, that the UPS not only survive earthquake-related forces, but continue to operate at the end of the event. So many 924 solutions are OSHPD certified, but other ones use calculations for seismic compliance, special mounting brackets, etc., and that may be acceptable to the owners and the authority having jurisdiction. So OSHPD is not required, but it is a desirable feature to have in an emergency lighting UPS, just like a data center UPS. So with that constitutes the main amount of information that we want to present here. I think now if we'll ask the moderator to go ahead and open up for questions, that would be fantastic, and we'll take those as many as we have available.
Thanks, Ed, for a great presentation. And now Ed will address some questions that were submitted throughout the program. Okay. Are lithium batteries used for emergency lighting?
We are looking hard at that, as are our competitors. You may have heard me mention back in the middle of the program there, a lithium battery is probably going to save between 40 and 60% in both footprint and weight. And the thing, of course, that stood in our way for so many years was the cost was prohibitive. You know, the lithium battery you use in your cell phone is relatively inexpensive, but that's an awfully small battery that's made in the millions and billions, as we all know. But we have seen dramatic reductions in the price of lithium batteries for this type of application just within the last couple of years, to where today I can say that a lithium battery is a viable option, and I would expect to see it from us and other emergency lighting vendors within the next few months. So it will definitely not cause you a cost penalty. It'll have a longer warranty on the battery and a much better size and weight profile.
What are the largest CapEx and OpEx differences between wall mount and UPS-based emergency lighting systems?
Primarily, if we think about CapEx, it's going to cost a bunch more to buy a big UPS with a big honking battery than it will to buy $100 or $220 emergency lights. So the CapEx is almost always higher for the centralized system. But the operational expense and the installation expense tends to be quite a bit more for the wall-mounted devices. I need to run a dedicated or a 120-volt circuit to each one of those emergency lights. So that's extra wiring that I would not have to do otherwise. For example, in a centralized system, I'm providing wiring to the light fixtures that are already in place, and I would have to wire anyway with regular utility power. Those are being fed now and wired by a dedicated panel fed by the UPS. But that cost is incrementally very small compared with the normal cost of lighting a building, whereas adding the emergency lights and the emergency exit lights and things like that means extra wiring that has to be pulled and run and tested and installed prior to getting authority to use the building safely. So the installation tends to be markedly less for the centralized system, and the month in and month out maintenance costs for monthly testing and even yearly testing is quite a bit less for the centralized system because I'm testing one machine rather than hundreds of small emergency lights.
Can the UPS power exit lights in addition to regular overhead fixtures?
Absolutely. The exit lights, if those are deployed, typically use 120-volt AC power. So the UPS can certainly distribute its output for those devices as well as or alongside of the regular lighting fixtures that are backed up by that UPS in a building. So the answer is yes to that.
I believe you mentioned this, but are there cities where local code specifies more than 90 minutes of backup power?
Yeah, that is a good question. If you talk to inspectors in large cities like Chicago and Los Angeles, for example, in the past, they had emergency requirements or emergency lighting requirements that were dictated by the local code and local authorities that had like 2 hours of battery backup time. And part of this is they know you're evacuating skyscrapers and things like that you may not be able to get out of quickly. However, the latest information that we have is that those codes have come into standardization with the National Electrical Code and the NFPA that dictate 90 minutes. So I think the answer is in almost every case 90 minutes is enough. But beware, the local code may show up and say, hey, I need an extra half hour.
please clarify how a UPS is different from a central lighting inverter system listed per UL 924?
That is an excellent question because the centralized or the emergency lighting inverter systems tend to have less cost, CapEx, than does a traditional UPS. An emergency lighting inverter is an inverter that's sized for whatever kilowatts that you need and a 90-minute battery system to power that inverter during a power outage. The difference is in the electronics that make up the battery charger. In a traditional UPS system, the rectifier/battery charger has to be big enough to support the inverter and the entire critical load 24/7, 365. So that dictates a fairly large and beefy rectifier. In an emergency lighting inverter, I don't really need a rectifier. I basically let utility power my lights until the power fails. And then the inverter comes on and draws off the battery for 90 minutes, and when power returns, I'm going to use a relatively small battery charger that just needs to be sized to recharge that battery within about 48 hours. So the cost to build that type of system is less. I do have a couple of concerns. It's a standby type system that says I need to depend on the critical moment when the utility fails, that inverter will start, that battery will be good and functional, and that the mechanical switching that takes place to connect the battery to the inverter and connect the inverter to my lighting distribution system, all of that has to work. So that's an element of risk that I would not have with a traditional double conversion UPS system that basically recreates its power all the time. But it is certainly worth considering the two alternatives because the cost is significantly different, and there's many vendors that make emergency lighting inverters that have been the more traditional centralized system for many years. What we have noticed as a traditional UPS vendor is we're getting more and more and more requests to use a conventional UPS for emergency lighting purposes.
Can you direct me on where it is required to have a genset outside?
Yes, I believe that was a part of one of the NFPA requirements, and as I was looking at that, I think that it may not be a firm requirement. I see it listed as a requirement, but I bet you if I go back to the standard, it'll say we prefer to have it outside for access. But if I'm going to put my 90-minute UPS in a closet inside the building, why can't I use an internally mounted generator to do the same thing? So that's a very valid question, and from my perspective, I don't really see a difference. So what I would have to do in this case is possibly take the information for the requester or have the requester contact me at edspears@eaton.com. That's EDSPEARS @Eaton, EATON.com, and I will research and provide the definitive answer there. But I believe it's in NFPA 110.
Would you briefly touch on the challenges that NFPA 101 requires 10 foot candle normal and 1 foot candle emergency on stairs and ramps? We get criticized from the architects owners on how expensive it is to light a 100-foot in-length ADA ramp, for instance.
That's right. That is a very good question, and I would certainly say that these kind of, shall we say, frank exchanges of views between the building owner who has to pay for all this and their design and lighting engineers who have to implement all this. But I typically have to agree that we do not want to compromise on safety, and I need to make sure that there's enough light even at the end of the battery discharge when a wall-mounted fixture may be getting a little bit dim, so that I have enough light to adequately exit the building. Then, of course, there's some subjectivity, as you can imagine, on what different people feel like is enough light. Different age of people and those kind of things may have a bearing on that question. So in the end, the NFPA is going to be the authority here, and folks like ourselves as a company and our competitors, we sit on the standards committees and we get input into this kind of information, but in the end, the decision is made by a group of people that agree on how much light is necessary. So there is a way or a route to change that, especially if it just becomes prohibitively expensive.
For wall or ceiling mounted units, what is the typical coverage to meet 1 foot candle average, 1/10 foot candle minimum?
That's something that we've looked into, and I know our competitors have as well, and it does vary, depend on how high the ceiling is, how high I place the lamp, for example, and those types of things. we know, as we said in the presentation, that we can assume that it's going to be about a quarter watt of UPS power per square foot. But if I'm not using a UPS, if I'm using wall-mounted devices, for example, then it really varies depending on the application. If I'm lighting a warehouse, I can mount the lights higher in the ceiling, harder to access for maintenance, but I may get a wider dispersion of light. I can pick a larger capacity device that has more heads on it or more lamps on it to create more lighting capacity as well. On the other hand, if I'm in an office building or a small commercial establishment, then I'm talking about lighting a lot more hallways, closets, bathrooms, those types of things, and it's going to require probably more of the wall mount devices. And so, depends on the application. Something like a big open warehouse or a manufacturing facility, I'm going to be able to meet the requirement probably with fewer number of emergency lights. In a more office cubicle or office space type environment, it's going to take more lights to provide the same benefit or the same lighting appropriately dispersed so that they can find their way down halls and out of restrooms and that type of thing.
Must a separate service be dedicated to emergency life safety applications?
Usually, yes. If I look at the codes, they are looking at powering these lights from a dedicated panel as opposed to using a portion of an existing distribution system or something like that. So most cases we see in a centralized system, the UPS output is feeding a dedicated panel or a series set of dedicated panels, and those panels are specifically providing backup power for light.
How does having a UPS replace testing equipment of lamps burn out?
The test basically does require that the UPS be placed on battery, and then someone needs to look out and make sure that the light fixtures themselves are functioning. So that's going to be a part of any kind of lighting test. But the actual test, the way it's described in the UPS operator manual, doesn't specifically say that you need to walk out and make sure the light is on, but that, from a common sense standpoint, would be a great idea. What the test actually requires is the UPS be placed on battery and that they verify that the UPS continues to operate with no utility power present, and when utility power is reinstated, that the UPS goes back to normal operation and that the battery charger in the UPS does start and function to charge the batteries.
How does having a UPS maintenance bypass affect required emergency system coordination?
Excellent question. And it depends on the type of protection devices that are used in that wraparound bypass. We have a choice, as do most of our competitors, to use anything from a molded case switch to an actual thermomagnetic breaker, but it does need to be coordinated with the upstream and downstream circuit. So I've got a maintenance bypass path that I need to coordinate all the protective devices on it, from the upstream protection all the way down to the breaker that feeds the lighting fixture. And I also, at the same time, have to coordinate the breaker that's closest to the fault with the upstream breakers back up to and through the UPS. Remember, the UPS will automatically go to internal bypass if it sees a fault or a short circuit. So at that point, the UPS becomes a straight wire with series fuses for coordination purposes. On the other hand, if I'm servicing that UPS and have it in maintenance bypass, then the switches and or breakers in the maintenance bypass become part of the list of devices that have to be coordinated. And again, coordination is not an option like in the old days. It's for this type of application, it is in fact required.
How often do the battery backup need to be tested?
Once a month for brief discharges, and I believe once a year for a full discharge all the way to battery system shutdown. So that we're talking about making arrangements for a 90-minute test of the battery system to verify that I have the full 90 minutes of capacity with my system. That's once a year.
What's the difference between an emergency lighting inverter and an emergency lighting UPS?
The emergency lighting inverter, like we mentioned a little bit earlier, has a much smaller AC to DC converter or battery charger, whereas a conventional UPS will have a very large AC to DC converter that powers the entire inverter and the critical load, in addition to being able to charge the battery at the same time. Other differences between the two, you're generally going to see more accurate control of voltage and frequency on a conventional UPS, wave shape of the sine wave, etc., which it can be argued may not be necessary for a lighting application. But we do see a lot of clients that are asking for traditional UPS here as opposed to just an inverter, which might produce a modified sine wave of one type or another. The likelihood, though, is that either source will work. So the big difference is in the upfront cost of the equipment and the situation we mentioned earlier where an emergency lighting inverter usually operates in a standby or a line interactive fashion where I have to depend on some level of mechanical device to function at the critical moment of a power outage. So many clients consider that an unacceptable risk. They want a device that constantly recreates new power on the output so that when utility power fails, the device simply continues to do the same job it's been doing since day one, just draws power off the battery rather than from the utility.
Are UPS units used with demand response programs?
Unfortunately, I do not know the answer to that question. I can look into it, and if you will send me an email at edspears@eaton.com, we will get an answer for you.
Are UPSs used for other things other than lighting, such as pressurization fans, etc.?
It's awfully tempting to do that, I know, but the latest versions of the fire code say that if you're going to use a UPS for emergency lighting, then that UPS must serve no other purpose. So I can't take my giant data center UPS, for example, and use it for emergency lighting, or my mechanical system support UPS system and use it for emergency lighting. So if I'm going to use a UPS, it has to be a dedicated UPS and only for lighting backup.
Does the full battery discharge test shorten the life of the batteries?
Yes, it does. That's why we don't want to do it any more than we have to. So the yearly full discharge test is going to have an impact on the entire service life of the battery. That's why we don't want to do it every month or even every 6 months. It would be our preference, and the requirement of the codes that it dictate is that a full discharge needs to be done once a year, so at least we know that we have the capacity that we intend. However, most power outages are less than 10 to 15 seconds, and the monthly test is going to cover that without providing undue stress on the battery system.
I think we have time for one more question. Let me see. What is the distance limitation from the centralized UPS? How far away can the lights be from the central UPS?
I don't have a firm published answer on that. However, it is not uncommon to see UPS emergency lighting distance in excess of 500 feet to 700 feet from the UPS. So in a large installation, I might want to consider operating the UPS in the center part of the building if possible, but I can go a long distance with AC distribution here, unlike DC distribution, if I need to, and it's even probably allowable to put a step-up transformer if necessary. If I have a line that wants to run over 1,000 feet, for example, then a small transformer could be put in place with taps to adjust and compensate for line drop.
Well, that's all the time we have for questions today. Please join me in thanking Ed Spears for his presentation, as well as our sponsor, Eaton. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple minutes to complete our survey. We strongly welcome your detailed comments. Please visit webinars.missioncriticalmagazine.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience.